an extreme event happen that leads to the failure of the structure, either a partial failure or a total collapse in the structure. There are many numerical analysis methods available in the market for doing structural analysis, and each one of them has its own advantages and disadvantages. For example, when we speak about the finite element method, it is very good when it comes to simulating or doing linear elastic analysis. Also, when you go to the nonlinearity of the structure, where you have cracking, yielding, and crushing, buckling, and post bucklings, this is also very good method to do your analysis. However, the engineer must do some assumptions in his model. For example, if you are using a simplified nonlinear analysis uh, method, like the common ones that we see in the market, you have to assign what we call plastic hinges locations so that you can track the behavior of the nonlinearity of the material at these plastic hinges locations. Also, you have to assign what we call the end offset, the rigidity of the connection itself, and how it's going to behave during the analysis. When it comes to element separation, debris falling, and collision, the FEM is not suitable for this kind of analysis because the nodes cannot be separated from each other. And the only technology that can do this is available with the high fidelity numerical models like LS-DYNA and ANSYS. But again, the user must predefine the cracking locations in his structure so that he can see the elements being separated and so on. Then there is the discrete element method, DEM method. It is very good in simulating the element separation, debris, and collision. However, it has some problems with the static analysis and doing quantum materials. And that's why we have now the applied element method, AEM, which is capable of tracking the structural behavior in the linear stage, cracking, yielding, crushing, buckling, and post-buckling, element separation, debris, and collision. And all of these are automated inside the technology. Now, the question is, why do we need to reach to the level of the element separation and debris and the collision? So there are many examples that we see nowadays that requires this type of analysis. For example, if you are doing an assessment for a building subjected to a blast load, then if you use the simplified methods for like doing SBEDs and so on, then you are solving component by component in your structure, and you are losing the advantage of the interaction between different components to resist the blast loads. Also, the progressive collapse analysis, we now have many federal buildings that must be designed to resist progressive collapse. And as a definition for the progressive collapse, that the structure, the federal buildings and the DoD buildings must be able to resist a failure that can happen to the column without progression of this failure along the height of the building or the length of the building. Also, with the forensic engineering, if you have a case like what we see in front of us here, the I-35 bridge, and you want to investigate why this building or why this bridge experienced a collapse. So this is also a very good application for the applied element method. The seismic analysis, either it is a new building or existing building, the technology has the ability to do time history nonlinear dynamic analysis, where you assign the earthquake that you are going to design your building for, and you can see the effect that will happen in your structure, and you can consider in your analysis either there is a corrosion that happened in the reinforcement rebars, cracking like pre-existing cracking in your building, and so on. There is also the fire engineering, where you have a building that might collapse due to fire. Impact, where you are having you have a building and you want to design it to withstand an impact load from a rocket or from a vehicle impact. So this is also very good application. And also in the event of you have like an extreme wind case that can lead to either a partial failure for something like a bridge here, uh, then you can see these effects inside the EAM technology. The video that I'm going to show right now, it is showing the Champlain Tower that collapsed back in June. And what we did in here is that we modeled the building using the as-built drawings that was available. And we assumed that two columns from the bottom floor are removed from the analysis. So the technology here allows you to track the behavior of the structure when we remove the columns from the bottom floor. And as we can see in here, cracking occurred at the slabs, and the failure began at the middle part of the building. And due to the catenary action, we see that the part on the right hand side followed the collapse until the failure, while the part here that it stands here without any damage. Now, let's speak about the nonlinear structural analysis that engineers do when they are doing a seismic analysis or progressive collapse analysis. For example, we have here a frame, a reinforced concrete frame, and there are some lumped masses on the beams. We can see also here the geometry and the reinforcement details of the beams and the columns in the first and the second floor, while the picture here is showing the structural geometry and the reinforcement details of the beams on the last floor in here. So engineers, when they are doing progressive collapse analysis or seismic analysis using simplified nonlinear analysis programs, so they have to assign what's called the plastic hinge location, where they define the behavior of this hinge location. uh, uh, they define what we call moment curvature curve, the behavior of the connection during the analysis. So here, for example, some engineers put the plastic hinges at the beginning and at the end of the members. Others will put the plastic hinge at the beginning end of the member as well as the midpoint of the member. Others will put it at the beginning and end as well as when there is a change in the reinforcement details. And others are going to divide the beam into several frame elements, and they just go ahead and define a moment curvature curve for each of these hinges. Let's check the experiment here and what happened when they removed a column from the first floor. So as soon as they remove the column from the first floor and they apply a push down analysis on the connection in here, so we see that the frame is moving downward, and we see here the cracking happened at the first and the second floor at the location of the curtailment of the reinforcement. However, at the last floor, we see that it happens near the ends of where you have the connections with the column. Continuing the analysis, we see the propagation of the failure. And because this frame doesn't have a, a lateral support resisting system, so we see that the catenary action and the normal forces in the bottom beam leads to a pulling for the frame inward, leading to the total collapse of the frame. We did the same analysis inside our technology by drawing the structural components, assigning the reinforcement details as you see in the drawing, and just remove the column and apply a push down analysis. We don't have here to assign any plastic hinge locations. We don't have to assign end offsets and so on. So I'm going to play the analysis, and we see here the bending moments on different beams. And we see that the failure happened at the location of the curtailment of the reinforcement at the first and second floor. However, at the last floor, we see that the failure happened at the location where it is having a connection with the column. Comparing with the load deformation, so we see here the load versus the deflection, and we see here a comparison between the experimental results and the technology results. So we could match very good the initial stiffness, the yielding load, the failure of the reinforcement tree bars at different location, followed by the catenary action and then the failure. This is a screenshot showing the final shape. And now let's speak about the technology itself and the method, the applied element method, and how it works. So the applied element method, it is a stiffness-based method similar to FEM exactly, where you subdivide the structural components like a girder or a beam or a slab into several solid elements. And then you connect the, the solid elements together with what we call material springs. The springs here represents the axial deformations as well as the shear deformations that happens inside the material. As an example, if we have a column like this, a concrete column, and we highlight on those two elements. So we have discretized the column into several elements in X, Y, and Z. And then we highlight on those two elements, element number one and element number two. So what happened here is that we generate between the elements at the interface between the elements a group of springs. When I say one spring, it is actually three kinds of springs that are generated. One normal spring for the normal deformations, and two shear springs for the shear deformations, one in XZ direction and one in YZ direction. With the same exact concept, if you have a reinforcement rebar that's going to pass between those two elements inside the column, in this case, it's going to be a stirrup. So we replace the reinforcement rebar at its exact location with, again, one normal spring and two shear springs, one in XZ direction and one in YZ direction. There are some minor differences between the applied element method and the finite element method. For example, if we see here in the FEM, we apply a tension load on this member. So we see here that the deformations are happening inside the elements. However, the nodes cannot be separated from each other. Here in the applied element method, the element itself is rigid, so no deformations are happening inside the element. All the deformations are happening where the springs are generated, so at the interfaces between the elements. So if you apply a tension displacement for 1 inch, so the total displacement here will be 1 inch. Also here, if you apply a displacement of 1 inch, the total displacement is going to be 1 inch. There are also, or there is a difference also in the number of the degrees of the freedom. So in the finite element method, if you are using a brick element or a solid element with 8 nodes, so you have 3 degrees of the freedom at each node if you are solving using FEM, leading to 24 degrees of the freedom for each element. Here in the applied element method, we have 6 degrees of the freedom only, and they are in the CG of the element rather than in the node, because we don't have nodes here inside the applied element method. We only have element and the spring. So 3 for the translation and 3 for the rotation. And this actually makes our solver 6 times faster than any FEM solver doing solid element analysis, because of the number of the degrees of the freedom are much less. One of the advantages also is in the FEM, if you have 2 elements that are overlapping like this is a problem in the finite element method. You have to have nodal compatibility between the nodes in here. Here in the applied element method, you don't have to have nodal compatibility. If you have an overlap like this, connectivity and springs are generated automatically, and the user has full control over the kind and the material generated in here. And this actually makes the meshing much easier in the applied element method. For example, if you have an area of a coarse mesh and an area of a fine mesh, then you have to have here a transition zone in the finite element method. In the applied element method, theoretically, if you have an area of a coarse mesh and area of a fine mesh, springs are going to be generated here automatically, and as I said, the user has a full control over the interface material between two members. All our material models that we use are non-linear material models. So for example, we see here the material models that we use for concrete, and it is fully path dependent model. Also for the steel, either they are reinforcement rebars or they are steel members. This is the material model that we use for the steel. And we have full library of materials inside. So we have concrete, steel, brick, mortar, um, uh, elastic material also exist, and all other materials that we see in the construction market. These all have pre-cooked material models inside. So finally, if you are having a case where you have a collapse in the FEM, you will see the element looks or the behavior looks like rubber more than actually failures that you see here in the applied element method or the ELS technology. Um, so I will stop here and ask if anyone has a question regarding the applied element method. If we don't have any questions, we will continue our presentation. Okay, so it seems like we don't have any questions, so I will go ahead and continue our presentation. So the extreme loading technology is divided into three parts. The first part is the modeler, where you can model the structural components inside, like columns, beams, slabs, pre-stressed members. All of these are having styles inside that you can use to build your model. And then you have the solver, the AEM solver, and finally the viewer, where you are being able to see what will happen to your structure in case of an extreme loading event that needs non-linear analysis. And the viewer here does not only show the collapse shape of the structure, it gets you stresses, strains, bending moments diagrams, normal forces, shear forces, and charts for like measuring the deflections and so on. For every analysis method, there must be some verification examples that prove that this is accurate. So I will begin by this example. It is showing a concentric braced frame under cyclic loading, where we have here two columns, beam, and then some bracing connected to the beams and the column using the gusset plate. And then they are going to apply a cyclic loading on this frame. We can see here the same example in the lab, and we can see here the ELS model that we created, taking into account all the structural detailing, the material properties, and the loading applied on the frame. The first shot here, or the screenshots here, are showing the cycles and the maximum load that the frame could handle. So the maximum load was around 234 kips. We see here the values that the maximum load was also around 234 kips. Also comparing to the load deformation, we see here the animation. This video is a direct output from the technology. This is not created using a tool or a video editing tool, this is a direct output. So you can see here the degradation in the stiffness after the buckling of the bracing, as well as the local buckling that happened near the column connection at both sides of the frame. We see here also screenshots showing a comparison between what actually happens. So we see here the, the, the local buckling that happened at the flanges. We can see also here the cracking that happened at the gusset plate due to the cyclic loading. And also here, this is a very good view for the buckling that's happened and the failure in the bracing due to the applied load. Also, one of the verification methods that we use is that we compare to actual cases. So, for example, we are showing here a, a demolition project that we were involved in, where the demolition contractor wanted to see the behavior of the structure when he's going to remove the structural columns from the towers, leading to the collapse of the building. So before the demolition, he wants to make sure that the building is going to fall according to the plan he have designed for the implosion. So we see here a comparison between what we have predicted versus the actual case that happened. And these are all our demolition projects that we do. We do the analysis before the actual event happens. So this is considered as if it is a blind test for the technology in the nonlinear structural analysis. Now, about the extreme loading technology itself and the graphical user interface, we have a very simple graphical user interface for doing nonlinear structural analysis. So inside the technology, you can model, as you see here, brick walls, RC columns, circular columns, RC beams, and this leads to a building or an example for a building as we see in here. Also, for the steel buildings, we can model columns, uh, the columns with the connections, even RBS connections, reduced beam sections, corrugated metal decks, cold formed steel, as well as screws that connects the metal deck to the track of the cold formed steel load bearing walls. And this is an example for a building with structural steel components. There are also some templates inside the technology for like the flat plate. You have also for the trusses, either they are like for the towers or roof trusses. You can also see here some templates for a hollow core slabs with pre-stressing inside them, segmental bridges, and all of these are templates inside the technology that you can use. I'm going to open the technology now and model this building very quickly so that you can feel how easy is modeling inside ELS. So I'm going to start building a model, just 4 columns, 4 beams, a slab, masonry wall, and a window in between. And then we are going to assign a blast load on it. First thing, I'm going to assign the units. I will choose inch for the length, and for the mass, I will use kips. And the first thing that I'm going to use is that I'm going to put here the maximum first story height. So assuming that the maximum story height, the first story is 150 inch, and click on OK. This will open up the main modeling window inside ELS, where you have here some toolbars for drafting, like drafting lines, rectangles, every component as you see in the CAD tools. And then we have here some components like drawing a column, drawing a girder, a slab, reinforcement rebars, masonry walls, windows, and then the steel members that we need to put. You can model either in the 2D view, as we see in here, XY, or in the YZ. I will first begin here with assigning the style of the column. So the technology here allows engineer to model components rather than element by element. Usually, when engineers using high fidelity numerical modeling like ANSYS or LSDyna, they have to model element by element. Here we model component by component, and then we subdivide this component into elements. As you can see in here, I'm going to put a column. So the column, it has geometry, it has reinforcement rebars, and the steel section if you have a composite member. For now, I will just assign the geometry. Let's assume that the column geometry is 12-inch by 12-inch and apply. And it has a material of the concrete. And then the reinforcement rebars, I will put here the number of rebars at each direction, putting also the cover. The area of the reinforcement rebars, let's assume that they are number 5. And they have material of normal steel. Now for the branches or for the stirrups, I'm going to assign 3 branches in each direction, spaced at 8 inches with a number 3 area. Apply and OK and OK. Now I'm going to click on the column and insert it inside the modeling window. We see that it comes with a default mesh, and this default mesh can be changed anytime. We can just change the view now to be solid and shrink to be able to see the elements. And I'm going to specify the number of elements in each direction. Let's assume 30 by 3 by 3 elements. So we see here a complete model for a column with solid elements. Then I'm going to take a copy from the column. Let's have it from this point, the midpoint, at a distance of 200 inches and 0. So we see here that we have 2 copies from the column. Now, if I go to styles, girder style, with the same method, geometry, reinforcement rebars, steel members, I'm going to assign the geometry of the girder. Let's put 12 inches by 30 inches. And let's assign the top reinforcement, bottom reinforcement, and so on. So we will assume that the bottom bars are for number 5. Top bars, I'm going to assume that they are 2, number 5 as well. And sidebars, let's put 1 sidebars with an area of number 4. And then the number of branches for the stirrups, 2 branches spaced at 8 inches with an area of number 3. And apply and OK and OK. Now I'm going to draw the girder. Let's go ahead here and draw the girder from the face of the column to the face of the other column. So we see here the elements. Let's change the view to be solid again and shrink. Display mode, solid, shrink. And then I'm going to assign the number of elements that I need for this beam. Let's assume they are 20 elements along the length, 1 along the width, and 5 along the depth of the beam. Now I can take a copy, or let's use the array command this time. 2 copies spaced at 200 inches and OK. And I just need now to close my room with some beams, snapping here to the midpoint of the column to the midpoint of the other column. And we can take a copy from this beam copy from this beam to here, and we can assign the elements for them very quickly, 20 by 1 by 5. And let's go ahead now and change everything to be solid and shrink. And now it's time to put the slab. In the slab, I will just assume that the thickness of the slab is 5" with a material of concrete. And I will put here slab reinforcement. I will put top and bottom mesh 1 bar every 12 inches at the top and the bottom. Each one of them is number 4. Apply and OK and OK. Now we can either again draw into 3D or the 2D. I will choose the 2D this time to snap to the corners here. And we have the slab with the reinforcement 3 bars that we assigned. Again, I'm going to go here, assign the number of elements needed in each direction, and the wireframe or the change of the display mode to be solid and shrink. Now I'm going to go ahead and model the masonry wall. In the walls, style number 1, I'm going to assume that the wall is 6 inches in thickness with a material of brick and the mesh generation as masonry. And then you can put here the brick information like the length, the width, the height of the brick, as well as the mortar material that's going to join between them. Apply and OK and OK. We can go ahead here and draw the wall that I have from the face of the column to the face of the other column in here. And then we can see here an intersection between the beam and the masonry wall. So I'm just going to reduce the height of this wall to take into account the beam. And now we can display this as solid and shrink. Solid and shrink. Now I want to create an opening inside this wall. I will just select one element and add an opening. So we see here that an opening has been created, and you can control this opening dimensions like the upper distance, lower distance, and the left and the right, as well as the width and the height of the opening. Let's put a window. I will just use the default one here to save the time. So we have here a window. I will just move it from the point here in the middle. Let's snap to the elements here, the midpoint of this frame to the midpoint of the wall in here. And I will just assign the number of elements needed for the glass. And now our model is ready to assign the loads and the material properties. Let's go to the material first. So as we said before, we have here library for materials. For example, the concrete material, where you can assign the Young's modulus, the shear modulus of the material, the compressive strength, the tensile strength, as well as the shear strength of the concrete. When you click on the plot stress and strain curve, you see here the backbone of the stress and the strain curve that we are going to follow during our nonlinear analysis. With the same concept, if you go to the steel reinforcement or the steel members, the steel model, you can assign the Young's modulus, the shear modulus, the specific weight of the material, the yield strength of the rebars. You can also assign the ultimate strength as factor from the yield, and then apply and OK. And now let's go ahead and assign the loading. I'm not sure if you can hide this part in here. See if we can move it. Okay. So let's go ahead and assign the loading. The loading inside ELS is done on stages. So the first stage of loading is applying the own weights and the live loads and so on. So you can apply here static loads or dynamic loads. As for the static, you can assign concentrated loads, displacement, hydrostatic pressure, uniform pressure, moving loads, and so on. For the dynamic loading, you can put here dynamic, and you can, let's keep this as static, and let's create a new stage of loading for the blast. So dynamic loading, of course, you can assign concentrated loads as an impact or displacement, earthquakes, blast loads, uniform pressure, and so on. And so we will speak about here the blast loads. And we are going to assign a very small time step so that we take into consideration the impulsive loading phenomena of the blast loads. And now you have to put the blast weight, the charge of your blast weight, and you can put here the explosive types as TNT or C4 or whatever material of the blast that you have. And now we are going to put the location of the bomb. I will just choose like the mid location of this room. So let's have it at the middle, and I will just put the height or decrease the height so that it is at the center of this room exactly. When you go to check, you see here that you have the information for the blast loads, the arrival time, the duration, the peak pressure, and so on. Apply. And one final thing before we go ahead and run is to assign how many steps of loading do you want to see in the viewer? Do you want to see at every time step or at every 10 steps and so on? Apply and OK. Now, the ELS assumes that there is a ground connected to the last element to the floor. So you don't have to assign here a boundary condition. The boundary conditions here, by default, they are fixed to the ground. If the engineer want to change the boundary condition to others, he just need to remove the ground from the analysis and go ahead and assign the boundary conditions for the elements connected to the ground. Either they are fixed or hinged or whatever boundary condition you have. I'm going to run the analysis now, and let's see the results of this analysis. Run the analysis. Few moments to get the solver screen running. So we are now at stage 1, applying the own weights, and then we begin by applying the blast loads. The good thing about this technology is that you don't have to wait until all the analysis is done to be able to view your results. You can view the results of your finished analysis and keep updating the viewer with new results every since and while. So, for example, we are going to open now the viewer, and we are going to play the analysis and see where are we so far. So we see here, because the glass is the weakest point in our structure, we see failure that's happening in the glass. We can see also, if we have like an elevation view, we can see the cracking that happened in the masonry wall. We keep updating the results. We see that the slide bar here move to the back. Keep updating again. We see here it's moving to the back. Now, let's show the cracking happening inside this wall. There are several ways to view the cracking in the structure. One of them is using the strain contours. If we go here to the strain contours, strain and stress, the principal strain contours are the best way to view the cracking inside your structure. So if we put here, for example, a strain of zero point 0.1, we can see here the contours representing the cracking in the wall due to the blast load. And by default, all the connectivity that's happening between the masonry wall and the members around it, these are all mortar materials. That's why we see here red areas where there is a separation happening in the mortar material. One thing also, or other output that you can get, we can get the, let's for example plot a chart between the time and the data displacement of one of the elements of the slab in the z direction to see the uplift. So we see here that so far we reached to around 8 inches, and it is keeping, or it keeps updating. Other output that you can get also is the bending moments for these beams and the columns. So I'm going here to the properties, choose to show the bending moment in direction 3, I'm sorry, in direction 2. And we can play the analysis and see the results of the bending moment. Maybe we can hide. We just try to move this. If we hide all the elements, we can view here the bending moments acting on the beam, and of course it is an uplift. Now, because of the time, I will stop the example for now and continue my presentation. So, is there any questions about the examples that I have shown now? Okay, let's move on to the applications. So the first application we are discussing, the blast analysis. There are several ways uh, for 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 putting blast analysis inside ELS. The first way is by generating the blast pressure using the UFC code for obtaining the blast loads, where we have programmed these charts inside the code so that the user would just put the bomb weight, the bomb location, and the explosive type, and the ELS will automatically detect the pressure, the arrival time, and so on. As an example, we modeled here the Oklahoma building that collapsed due to a terrorist attack. And we see here a comparison between what actually happened to what the ELS has I predicted. Another way is by importing blast pressure. If you have your own blast pressure, you can show it, or you can import it inside ELS, where we can see here it reinforced the concrete column subjected to a blast load, and we see here the deformations happening as well as the exposure of the reinforcement rebar and the spalling of the cover. Another way, by importing CFD analysis inside ELS. So our technology can read CFD output from the blast foam or open foam, and you can do more accurate blast analysis if you import CFD inside ELS. So we see here an example for a building where we did the blast analysis or the blast loads using open foam, and then we imported it here, and we see here the blast wave, including the positive phase and the negative phase. Of course, you don't have to assign plastic hinges formation. Strain rate effect, it is automated inside the material. The kind of output that you get is not only deformations, but stresses and strain, internal forces diagrams, and so on. I'm going to skip this verification example. It's just a very basic example for a curtain wall subjected to a blast load, and we compare the analysis results to what we see, to what happened in reality. So the red line represents the deformations that happening inside the glass window, while the yellow line represents the deformations happening in the mullions. And we can see here output showing the cracking that happened inside the curtain walls. Another view here is comparison between what actually happened in the deformations. So we see here the deformations that are happening in the glass window, and it is similar to what we see in here. Also, some screenshots showing the final cracking shapes. And this is a comparison between the experimental results and the ELS in terms of deflection of the center mullion, where we matched here the initial stiffness and the failure or the maximum deflection that the mullion experienced. Another example for the oil and gas industry with the blast, we have here a well protector, and we subjected it to a blast load, where we can see here the lateral torsional buckling that's happening, and the local buckling that's happening in the flanges and in the web. Another view in here is showing the stresses and the strains. Maybe these are the stresses, and we can see here the location where the stresses are exceeding the maximum. For the progressive collapse analysis, of course, we are doing nonlinear structural analysis using nonlinear material models with automatic plastic hinges formation. Membrane action and P delta effect is already included in the technology. Plastic rotation calculations are output. Debris loading. So in case you are familiar with the progressive collapse code, the new progressive collapse code becoming by the end of this year will allow some failure to happen in some locations inside the structure, but the engineer must take into consideration the effect of the debris loading. So for example, if you are solving a case for a three-story building and you are removing a column from the last floor, then you have to consider the debris falling from the third floor on the second floor as a loading scenario inside your analysis. Also as a verification example, we have here a 2D frame with infill masonry walls inside them, and they are removing a column from the first floor. We can see here the failure that happened at different locations. So we see here failures that happened at the location of the curtailment of the reinforcement and separation that happened between the infill wall and the concrete beam above. This is a comparison between what actually happened to the prediction of ELS. So we have here rebar fracture as this location, and this location, and these are all exact locations that we can see in here. Also a shear failure that happened at this beam near the connection with the column. And also we see here a comparison between the experimental results and the ELS results, not only from like the load and the deformation, but there is also a relation between the vertical movement of the frame and the horizontal movement of the frame. So at each floor, they measured this relation. LVTT1 is at the last floor, second floor, and first floor. So we see here the comparisons, and they are matching very well. Another example for a pre-stressed precast building subjected to a progressive collapse, where we see here failures that happened in the precast connections. And we see here in the next or in the next video, you see here the propagation of the failure along the length of the slab in here and the punching shear failure at the back. Another example which shows the effect of the catenary action on a structure. So we have here a cold formed steel building, and they are removing a load bearing wall from the first floor. And because there was no enough shear walls in this building, we see that the slab was strong enough to pull this building, leading to the total collapse of the building. Another view, close-up view, showing the technology, showing here the buckling and the post-buckling happening in the cold formed steel studs. Another application is a forensic engineering. So we have here a case for a porter frame, and we added here lateral load. We see here that there was a deficiency at the connection between the anchor bolts and the foundation. And we see here that the anchor bolt was pulled from the foundation. Another example is the I-35 bridge that collapsed in 2007. We see here an animation or a video, structural analysis video showing the behavior of the frame. This is another view showing the shear failure that happened at the connection on top, leading to the collapse of the whole bridge. For the seismic analysis, we have here the Pine Gold building in New Zealand that collapsed due to an earthquake. And this is the collapse shape of the building. We created an ELS model for the same building, and the ELS is being now used in the European Union to detect the cavities inside buildings after an earthquake or after a major accident that happens that leads to the collapse, so that the first responders can go ahead in the cavities location and try to rescue the people inside. The Fraunhofer Institute of Technology was also involved in this, where they did an LS Dyna model for the same building. And we see here a comparison between the real collapse shape versus ELS versus LS Dyna. So we see here that the LS Dyna could not get the same results as the real case. Plus, it took 288 hours for the solver to finish this analysis using a supercomputer. Our analysis took only 3.5 hours using 6 processor machine, and the 6 processor machine is now as if it is a regular computer. We did also strengthening for the core of the building using FRP, and we see here from the analysis that the building could survive this earthquake. Another example is showing strengthening or the effect of having shear walls as masonry walls inside a building. So this is a time history analysis. And we see here some failures that happened at some locations near the windows. I'm going to skip some examples here for the time. This is for the wind. So a car shed subjected to a dynamic wind load. Another example here for corrosion. If you have an existing building and you want to check the capacity of this building or this member under a corrosion effect. So we have here an example for a reinforced concrete beam with a pre-stressed cable inside it, where first we are going to solve it under a concentrated load in here, and we will see the behavior and the capacity of this beam without applying any rusting. So because this is a pre-stressed beam, so the deflection is going upward from point 1 to point 2. Then we apply the concentrated load here and we get here a failure load of around 60 kip. Then we repeat the same analysis again after assuming rust at, at the pre-stressed cable inside. So again, from the point 1 to point 2, we did not yet apply any rust. So the deflection is going upward. From point 2 to point 3, we are going to load the beam until certain load. We will begin here apply the rust by weakening the area of the reinforcement rebars representing the pre-stressed cable. So the deflection is going to increase a little bit up to the point 4, and then we will continue loading this beam up to failure, and we will see here that the capacity reached to around a 52 kip. So it went from 62 kip to a 52 kip. We repeated the same analysis again, but with strengthening the beam with FRP plate. So from the point number 1 to point number 2, going upward, I'm just going to skip some videos or some frames in here. From the point 3 to point 4, applying the rust. And then from the point 4, we are going to apply the concentrated load again. And where the location of the failure happened, we will add the FRP at this time. And we will see that the capacity of this beam reached now to be 80 kip. Impact analysis, we have here a slab subjected to an impact load from a projectile traveling with a velocity of 165 meters per second. And this projectile is going to impact the slab. We see here from the testing that the projectile is going to penetrate the slab, but it is not going to perforate from the other side. And the damage region here is 170 by 190, and the penetration depth was 50 millimeter, exactly as the depth of the slab. There are some hand calculations method for predicting this. The hand calculations showed that the penetration is going to be only 30 millimeters. The ELS, when we did the same analysis, it showed exactly the same as the testing results, as well as some differences between the scabbed region or the damaged region at the back. This video is showing the simulation for the impact and the damage that happened to the slab. Excuse me. This is a screenshot showing the damage that happened to the slab, and see here that the reinforcement rebars was not damaged from the penetration, and here also the reinforcement rebars was not damaged from the impact. This is the scab or the damaged region at the back. Another example here in the oil and gas is that there was a projectile with very heavy mass impacting a steel plate, and they want to optimize this steel plate so that it has the minimum thickness as so that there is no perforation that happened from this projectile. So we did some studies on this case, and we reached it to that the minimum thickness needed for this steel plate has to be 1.5 inches. The final application will be speaking about the fire analysis. So we have here a case for a reinforced concrete beam. They are going first to impact it with a hammer, and they, without application of any weakening due to the fire loading. So we see here that the impact, we see the damping that happened after the impact. I'm just going to skip some frames here for the time. This is a comparison between the experimental results and the ELS results in case of the impact for the deflection. Sorry. and then they are going to repeat the same example again, but after applying or after putting the beam in an electric furnace, and we will see if there is an effect for the fire on the capacity of the beam. So we see here the impact, and because of the fire loading at, at the bottom, we see failure that happened in the beam. And this is a comparison between the experimental results and the ELS results. One other example is for the fire loading. This is a frame where we apply a fire loading here at the bottom. We see here buckling happened in the column, followed by failure at the connections here. Another verification example for the fire, this beam has been exposed to a fire for underneath here, and then they loaded it with concentrated loads here, and we see here the lateral torsional buckling that happened to the beam when they applied the load, and this is a comparison between the experimental results and the ELS results. I think by this we reached to the end of our meeting.